So, welcome back, everyone. Here's what's on the docket for today. I'd like to, if all goes well, I'd like to at least get as far as mentioning nomenclature of alkanes. Before then, we have to talk about some facets of the structure of alkanes and other hydrocarbons, and also go through the idea of functional groups. You know, functional groups are pretty important. Functional groups are, I would say, if I had to define them off the cuff in my own words, I would say functional groups are pieces of molecules, certain atoms bonded together in certain ways that are by definition always a certain way. And whenever you see a certain functional group in any molecule, even if it's a molecule you've never seen before, you can draw some conclusions about what that molecule will do, how it will behave, what sort of properties it may have, what sort of reactions it will undergo. And little by little over the next 2 semesters, we're going to fill in the blanks there about how each of the different functional groups behave. A lot of these functional groups, of course, are found in biological molecules. So it's important to get all that right. I'm trying to think, I had roughly 3 announcements here. Let me see. First of all, just so you guys know, I have ordered the face mask. I listened to the video, the audio a little bit when I uploaded the videos to YouTube yesterday, and I'm really not happy with how I sound behind the mask like this. I also am concerned about people who may be hard of hearing or have trouble hearing. I've already had a few students in other classes come up to me saying they kind of rely on lip reading. Of course, with the mask on, that's gone. I would say, if that's you, that Zoom is allegedly taking real-time or making real-time captions. Their captions are okay, they're not bad, but I've actually heard that the ones that YouTube also makes are actually pretty good. I mean, it's probably going to fail on some of the scientific terms, but at least we'll have that until the face shields come in. We'll try it that way too. I probably am not going to be able to make everyone happy, but my goal is that as many of you as possible can actually get something out of being in class and listening. So I hope I kind of am not too optimistic about having the face shields as soon as Monday. Hopefully they come in on the weekend. It's possible, but hopefully by sometime next week, we'll be able to give that a try. We'll see how it goes. What else? Also, again, all of you who are present either in person or on chat, please register your attendance using the Reef Polling app. I do want to make it worth your while to actually have the app, but realistically, in the past, I've really only had about 2 honest-to-goodness polling sessions with answering questions per week, since often I would teach Tuesday, Thursday. So to take out the time to do it that way, I want to be sure that I can do the material justice today. So I'll try to avoid simply taking attendance more than once per week. That also gives me the opportunity to get you some practice problems up on eCampus, because I'll post the clicker session. So I think only good can come from that. But today I'm just a little worried about getting through everything in time without having to talk at 100 miles an hour more than absolutely necessary. So we'll just take attendance today. So anytime you like, I'm going to leave that open for the rest of the class. Speaking of Reef polling, one thing, if you look at your Reef grades right now, they're going to be all messed up. I have yet to go in there and fix everything so that everyone gets credit properly. I've never done that before for iClick or Cloud, but I have to think it's similar to iClick or Classic. That is my project for the weekend, is to get all that done so that everyone's grades are correct. And I also have to mark some excused absences, things like that. So don't panic when you see your grades. They're not correct yet. And in general, it might take a day or 2 for them to be correct. but I'll try to figure that out over the weekend. And speaking of the weekend, one last thing. I'll try to send an email out about this later. It seems that there is indeed some demand for me to have Saturday office hours. So at the moment, I'm thinking of noon to 2. You can zoom in if you like. I'll be at home. But I'll try to remember to send out an email about that later today. So that's sort of what I'm thinking. It's not like it's any trouble to me. I'll be around. Okay. So with that, I think we can get into the material. So I've already mentioned functional groups. I think before we get into the real heteroatom-containing functional groups, and by the way, you may have noticed that we organic chemists are terribly prejudiced in that regard. To us, it's like there's carbon and then there's heteroatoms. There's all the rest of the periodic table. And that's the term we use. So heteroatoms are things like oxygen, nitrogen, phosphorus, sulfur, chlorine, the other halogens. So the term heteroatom simply means it's not a carbon or hydrogen. So you might run into that term. If any of you ever go on and take inorganic chemistry, you'll find exactly the opposite. They're all concerned about the metal that's in the middle. And all of those neat organic ligands, that's just sort of spinach that sits around on the outside. So it all depends on your perspective, I suppose. But be that as it may, before we get into the heteroatom-containing functional groups, I'd like to at least take care of the hydrocarbons themselves. And I think the term hydrocarbon is pretty self-explanatory, right? It's a compound that contains only carbon and hydrogen. And I would say there are 4 flavors of such compounds. You've got, first of all, the alkanes. And I would say an alkane is, you can say it a couple different ways. You might say an alkane is a fully saturated hydrocarbon. What that means is there's no multiple bonds. There's only carbon-carbon single bonds and carbon-hydrogen bonds. And yes, if you wanted to, you could break down alkanes further into normal alkanes and cycloalkanes, the ones that contain rings. And we'll get to those as well. We'll talk about cycloalkanes at some length. But one thing that I'm still sort of working on how to explain, I'm always trying to get better at this. And I've talked with my colleagues about this, but the question of, is alkane a functional group? I don't know that I'm really that comfortable saying it is. The way organic chemists think is that alkanes are kind of like the base that we build all other molecules on, or the things that we then add functional groups to. We almost think of it as that an alkane is the absence of all functional groups. I guess the reason I'm bringing it up is you'll probably find yourself in situations on the exam or on OWLs where you're shown a molecule that you've never seen before and that has a bunch of functional groups on it. It's not really fair to pick an alkane portion of the molecule and say this is an alkane. I shouldn't say it's not fair. It's just not how we think. So, I mean, I think you know I think you can tell how I think about this by now. My goal is never to purposely be tricky or to try to lead people astray on exams. I try to keep things straightforward. It's not my goal to be tricky. But I just thought I'd mention that. Generally, if there's even one functional group anywhere in the molecule, it's no longer an alkane. That being said, these other 3 types of hydrocarbons, I really guess we could consider those to be functional groups because we've deviated from only single bonds, only carbon-carbon single bonds and carbon-hydrogen bonds. And I don't know why, maybe because it's Friday. I'm actually going to do a little experiment here. Oh, I forgot to say. Not aromatic. That's important. Okay, we'll add that in. So usually we introduce alkenes first, but it leads to a bit of a hiccup later on. And I think I might be able to avoid it by mentioning aromatics first. Oh, I should at least give you a few examples of alkenes. Well, any molecule you can draw that's all carbon-carbon single bonds and carbon-hydrogen bonds, you know, you can very much go crazy here. Any of these would be, anything like that would be an alkane or a substituted cycloalkane. They would all fall into that category. The smallest possible alkane, I suppose, is methane, CH4. One of the things we're going to be doing to help us learn how to name alkanes, which we'll start with naming alkanes. And the great thing is, once you have the system down for naming alkanes, really you can name anything else. I would say if you know how to name any simple alkane or cycloalkane, you already know at least 85–90% of what you need to know to name any molecule with any function. So it's worth talking about, but I think we'll spend some time talking about that probably on Monday. I don't think we'll quite get that far today. Good, so all that being said, methane is the first in a series of straight chain alkanes. And I'll just say now, so you're prepared for Monday, you'll find a table of common straight chain alkane names. Straight chain meaning that all of the, this molecule here would not quite be straight chain. It's got a branch on it. So it's all of the molecules that just have hydrocarbon alkane chains with no branches in them. We call those straight chain alkanes. And you'll find a table, as I said, of the names of a bunch of them going up to arbitrarily, ridiculously many carbons. I think it would be good if you knew, let's say, up to at least C12, dodecane. And I don't think you'll find that too difficult to learn. The only irregular names are the first four: methane, ethane, propane, butane. Those are C1 through C4. And probably at least 3 of those you've heard of. Propane you've certainly heard of. You know you can go buy a propane tank. And butane has a number of uses. It's used in cigarette lighters, for instance. After that point, the names become regular. They take the Greek prefixes. So penta, hexa, hepta, octa, pentane, hexane, heptane, octane, nonane, decane. And then when we go above 10, 11, and 12 are undecane and dodecane. I would be shocked if you ever need anything longer than that, though who knows? Owl will be owl. But the great thing is if you know up to C12, you kind of get up to C19 thrown in for free. So it's undecane, dodecane, and then as you would guess, tridecane, tetradecane, pentadecane. The remaining names make a lot of sense. So like I said, I just can't think of a situation I've run into where I needed to use one of those names longer than dodecane. But the great thing is, even if you do, they're pretty straightforward up to C19. And I really don't care if you can tell me what the C35 compound is called. I can't imagine we'll ever need that. I can't think of a case where we ever have. Good, so much for the alkenes. Let's try an experiment and let's talk about aromatic compounds next. Aromatic compounds really are going to be a subject we'll study in chapter 14 and 15 next term. So we'll get to the chemistry of those compounds. The situation is a little more complicated than that, but we can fill in the blanks later. For now, I think it's good enough for us to observe that benzene is sort of the archetypical aromatic compound. You can draw it with either alternating single or double bonds, or I actually often use a circle like this. You can do that too if you want to. I might have already given you the warning, though, that if you ever see any printed material from me with structures in them, the program I use is called ChemDraw, and ChemDraw makes it pretty hard to draw benzene like this. So in exams or class notes or what have you, you'll see my benzene rings looking like this. I don't really care which way you do it. They mean the same thing. The only time it's going to matter at all is next term, when we learn about the chemistry of these things and start doing arrow pushing and drawing mechanisms. Then it might matter. I don't think it's going to be a big deal either way for us here. And so we can also define as being aromatic any compound that includes a benzene ring. So I don't know. We'll put an isopropyl group up here. Maybe just for fun, we'll put an OH group over here. So this compound would be aromatic and would also be an alcohol. In fact, aromatic alcohols are called phenols. But we'll get to alcohols shortly, which brings up another important point. It's funny when you get to this topic that ideas just start coming out at this rapid rate. So we'll try to keep, the can of worms from going too crazy too quickly. But this does bring up another question, which I'm sure a lot of you are thinking. Can a molecule have more than one functional group? Absolutely. It happens all the time. Any of your biologically relevant molecules will have dozens or, in the case of proteins, maybe hundreds or thousands of functional groups in them. So sure, that happens all the time. And if you are asked, what kind of compound this is, you should say it's aromatic and an alcohol. I don't think you will ever be asked, which is it, aromatic or alcohol? Because the answer to that question is yes. Does that make sense? I'm just trying to get you ready for what to expect. Again, I try my best not. I can tell you that I never ask exam questions that I think are unfair. Sometimes I screw up, that's certainly true. But it's never my goal to ask a trick question. So aromatic compounds are hydrocarbons or substituted hydrocarbons that include a benzene ring. And I think that will be good enough for now. Questions so far? Also from chat. As I like to say, you mean I did it again? You mean I'm such a good teacher that no questions are even possible? I wish, in my dreams, I wish that were true. Okay, so let's take care then of alkenes and alkynes, and that will finish us up for hydrocarbons. So what do you mean by lead? Contains a benzene ring, I think I said. At least I hope. I'm saying an aromatic is a compound is one that is either benzene or contains a benzene ring. Is that kind of what you meant here in chat? Yeah, I don't think I hope I didn't say please, although, again, it's stupid. I said I wouldn't complain. This mask does make it difficult, but it is what it is. Okay, oh, contains, yes, yep. What is the circle in the middle of the benzene? That is a shorthand for the 3 alternating double bonds. And the reason we do that is because benzene is a resonance-stabilized species. The double bonds aren't really double bonds, in fact. You can draw another resonance form that has the double bonds and single bonds in the other alternating positions. So that's what the circle is meant to show. And some people like the circle, others don't. You choose whichever you like. I have no preference. But like I said, benzene is special. And the reason we're pointing this out about them not being really double bonds is because of alkenes. And I just want to be sure that we're not confused about that. So alkenes are going to be any compound that contains at least one carbon-carbon double bond and is not aromatic. So aromatic compounds are not alkenes. And we'll learn next term, as I said, that their chemistry is completely different. So benzene is not an alkene, but any other compound that contains at least one carbon-carbon double bond would be an alkene. The simplest possible alkene happens to be called ethylene. I don't really care if you know these things. I mention that though because you've probably heard of ethylene. Certainly you've heard of polyethylene, which is the polymer that comes from ethylene. That's used by the ton every day. Look at every soda bottle. Even the bottle caps are made of cross-linked polyethylene. But again, the molecule can be arbitrarily big. And as long as there's at least one double bond, you've got yourself an alkene. Can you have more than one double bond? Absolutely. Certainly that's allowed. That would still be an alkene. But as long as it has at least one carbon-carbon double bond, other than benzene is not an alkene. The compound is an alkene. And likewise, alkynes are compounds that contain at least one carbon-carbon triple bond. So the simplest possible alkyne would be acetylene, C2H2. And again, I don't care if you memorize these names, but you might have heard of acetylene. Acetylene is used in acetylene torches. These are used for welding, so it burns with an exceedingly hot flame. And you can do heavy-duty welding with an acetylene torch. But again, oh heck, let's even put in a benzene ring, why not? Well, I'm being a little naughty, not showing that as being linear, but it's not too bad. I'll give that structure a B-. So this compound would be both aromatic and an alkyne. That is both functional groups. And with that, I think we're done with hydrocarbons, and we're ready to go on to the heteroatomic functional groups. Good. Any questions before we do that? Yes. No, it is. Alkyne is a functional group. I'm just not sure that alkanes are functional groups. Yeah, alkanes really, to me, it sort of implies the absence of all functional groups. Yeah, but I would say the other three, aromatic and alkene and alkyne, those are functional groups. Good. Other questions? They just happen to be hydrocarbon functional groups. Now we can start adding heteroatoms, and that's when things get real. And real interesting also, I hope. See, I don't want to just delete everything because I want to leave that up there saying, please register your tenants. Okay, let's see. Let's also get rid of this if we can. I wonder if you can select and say, just delete all this stuff. The book used arome instead of aromatic. Which terminology can we expect to see on the tests? Any of them. Any words that are used in the book, I expect that you will know them. And it is sometimes a little annoying. I think I've said that organic chemists are never happy until there's at least two words for the exact same thing. So is there supposed to be a question and read for us to answer for attendance? No, we're just registering attendance today. Good. So again, I've actually put up some old exams, so you can look at them and get an idea of the sorts of questions I've asked in the past. But yes, I would say every word that's used in the book, you should know what it means, even in these cases where there's multiple words meaning the exact same thing. Good, okay. So where shall we start with functional groups? And there's certainly more than one way to skin this cat, so to speak. But maybe we'll begin with alkyl halides. And actually, here we go. These are also called haloalkanes. So there you go. There's two words for the exact same thing. And I don't really care which word you use. You might see al use either or both of those words. But I would say an alkyl halide is what you get when you take any hydrocarbon and replace at least one hydrogen with a halogen. Another way to think of alkyl halide, this is where they start using this R terminology. You probably noticed this in your reading. This R group over here is meant to be a shorthand for any hydrocarbon group, any alkyl group, as we'll start to call it. So R is kind of like X in algebra. And actually, I actually used X, and maybe that was a bad idea. So let's say RF, RCl, RBr, or Ri. So basically what you've done is you've taken any hydrocarbon and replaced at least one hydrogen with any halogen, fluorine, bromine, chlorine, or iodine. As long as you do that, you've got yourself an alkyl halide. So the simplest possible alkyl halide might be something like chloromethane. Here the R group is CH3. But again, this can get as large as you want and as complicated as you want. I don't know. Let's put in 2 bromines just because we can. Get the pointer out of the way. That would certainly be an alkyl halide. I guess pretty soon we'll be able to call that 4,4-dibromo-2-methyl-hexane. How does that sound? Something like that. That's what we'll get to on Monday. So anything like that, if you replace any hydrogen with at least one halogen, you've got yourself an alkyl halide. Alcohols are similar. And I think I have something like 3 spelling pet peeves when it comes to functional groups. Pet peeve number 1, there is only one H in alcohol. Please and thank you. I always get alcohol. It drives me crazy. So only one H in alcohol. You could consider an alcohol to be essentially ROH. Alcohols are organic derivatives of water. You can also think of it that way. So the group R Again, that's like an unknown. It's like an X in algebra. The group R can be any hydrocarbon group. The main thing R cannot be is hydrogen. And sometimes for these definitions, it will be okay if R is hydrogen and sometimes not. So that will be important to know. Oh, I'll also just say, maybe before I get into too many functional groups, a couple other pointers on what you'll need to know and how to know whether you know what you need to know. There is, of course, a table of all of these functional groups in the book. I can't in good conscience recommend that you memorize that table. Knowing function, first of all, you will need to know all the functional groups. You know that already. But knowing the functional groups doesn't mean just memorizing that table. And I've put all this in the class notes. I've defined in the class notes what it means to me to know functional groups, so that you know what you have to know and you know what to aim for. But among other things, I would say knowing the functional group, and like this is all in class notes, knowing the functional group means that you can recognize any of these functional groups, even in a molecule you've never seen before, no matter which direction it points and no matter which structure drawing method is used to draw the structure. That's what it means to know a functional group. You should work to be able to say, I've never seen this big, ugly, godforsaken molecule before, but this over here is an alcohol, that's an aldehyde, and over here we've got an alkene. That's the sort of thing to be able to aim for being able to do. Does that make sense? So, I mean, memorize the table if you want to, but I don't believe it's a good use of your time. Good. Okay, so alcohols are organic derivatives of water. So, of course, R cannot be hydrogen, because if R is hydrogen, you have water, and water is not organic. The simplest possible alcohol would be methanol. You have to give at least one carbon for it to be an alcohol. That's the smallest possible one. Methanol is also called wood alcohol. It's actually very toxic. It showed up in the Prohibition days when people were making, stuff in their backyard, and it would always be contaminated with some methanol, and people were drinking it, and then it would die. So it's a problem. It's very, very toxic. The next alcohol would be ethanol. That is, of course, the intoxicating component of adult libations. Certainly a little toxic also, though nowhere near as toxic as methanol. But again, it can be some goofy molecule that you've never seen before. I don't know, let's just go crazy here. I would expect you to look at that and say, I have no idea what that stupid thing is, but it's definitely an alcohol. I see an OH group attached to a hydrocarbon bond. Make sense? Yes. The question is, how would I define an organic derivative? By organic derivative, I mean that you remove an H and replace it with a hydrocarbon group. So organic derivative means you take something and you remove an H and you replace it with a hydrocarbon group. Other questions? Mind you, I made up that definition off the top of my head. I don't think I'm going to fall into the ditch, but we'll see. Good. So after alcohols, I think we should do ethers. Ethers are a little bit similar to alcohols in some ways. They're really another organic derivative of water, but I would really define an ether as being an oxygen that's attached to two alkyl groups, two hydrocarbon groups. And those two R groups can be the same or different, doesn't matter. But once again, neither of those R groups can be hydrogen. Because I think you can see, if either one of those R groups is H, then you don't have an ether, you've got an alcohol. Make sense? So the simplest ether, I suppose, would be dimethyl ether with two methyl groups, CH3s over here. That compound is used sometimes, but not really a lot. One of the more common ethers that you'll get to know is diethyl ether. this compound is actually sometimes colloquially called just ether. And it's a very, very commonly used industrial solvent. But again, those two groups don't have to be the same. You can have the two groups be different. You can have a terphenyl group on one side and a methyl group on the other, let's say. So this, by the way, you can see it's a carbon here and the 3 CH3s. I think you'll learn shortly that guy's called a terphenyl group. And I don't care if you know this, that happens to be called MTBE or methyl terphenyl ether. It was used for a while as a gasoline additive in order to increase the octane rating, but it's unpogotoxic and not all that great for the environment, so it fell into disfavor. And mostly people add ethanol now instead of methyl terphenyl ether. Ethers can be cyclic. The oxygen can be included in a ring just by connecting R1 and R2. That's certainly allowed. So something like this would also be an ether. It's supposed to be a 500 ring. Yeah, that would certainly also fall into the same category. We'll meet that guy later on too. That's also sometimes used as a solvent. So again, knowing what an ether is doesn't mean memorizing R1, R2. That's not knowing what an ether is. Knowing what an ether is means, again, that you can pick it out, even in a molecule that you've never seen before, no matter which direction it points or anything like that. So that's it for the main oxygen-containing functional groups, at least until we get to the carbonyl-containing ones. And I have until 11:30. Yeah, it's like I said, I wasn't sure I was going to be able to get. I'll try to at least get through all of these functional groups. I made the right choice not having a real reef section. Good. Let's do amines next. A-M-I-N-E. And I will tell you, I am pretty much always unhappy with how amines are defined in these tables of functional groups in organic textbooks. I think the best way to define an amine is like that. That it's an organic derivative of ammonia, actually. So you need to take, ammonia is NH3 and ammonia is inorganic. What you need, as long as at least one of the hydrogens is replaced by an alkyl group, then you've got yourself an amine. The others can still be H's, or they can be other alkyl groups that are the same or different. But you do need at least one in order for it to be organic, in order for it to be an amine. And so I guess the simplest amine would be methylamine, CH3NH2. You can't get an amine any smaller than that. But, you know, this can be arbitrarily big once again. The groups can be the same or different. There can be 2, 1, or 0 hydrogens directly attached. If you replace this hydrogen with yet another alkyl group, that would still be an amine. So anything like that, that has regular hydrocarbon groups attached to the nitrogen. Anything like that, you've got yourself an amine. But I mean, I really do think that's a much better definition of amines than what you normally see. Yes? But the question is, what will I do in exams? Will I ask you to find functional groups? I might, and again, I posted old exams so you can see, but I'm not going to commit to any particular question formats. Probably on any given exam, you'll get a question that's of a format you've never seen before. But I did put some old exams up so you can get an idea for the sort of things I ask. Certainly that would be fair game. That would certainly be, and I think we'll get questions like that in OWL also. Okay, other questions then. Let's see, so we did amines. Nitriles don't get too much play, really, but nitrile, N-I-T-R-I-L-E. Nitriles are actually organic derivatives of hydrogen cyanide. So RC triple bond N. And they get some use. They're not used a lot. We'll learn more about them next term. I don't think we'll talk about them very much here. Simplest nitrile would be acetonitrile. And again, I don't care if you know that that's what it's called. This is supposed to be a lone pair. But the methyl group can be any alkyl group, and you would still have an a nitrile. So it's interesting because it's another functional group that includes a triple bond. Oh, another thing I should probably say, quadruple bonds are not a thing, in case you were wondering. Single, double, and triple were fine. Quadruple, not a thing. Good. And with that, I think we just need to take on all of the carbonyl-containing functional groups, of which there are about 5. So first of all, I just want to point out that the C double bond O itself has a name, regardless of what else is attached to the carbon, and that's called the carbonyl group. Carbonyl, carbonyl. It's not carbonyl and it's not carbonyl, it's carbonyl. Carbonyl group is almost a functional group in its own right. Certainly, if you want to point at a place in the molecule that there's a C double bond O and you say that's a carbonyl group, you'd be completely correct. But there are about 5 functional groups that themselves contain the carbonyl group that we need to cover. And so that's what I think we'll be spending most of the rest of the time. And again, I would say the reason you need to know these is we're going to use these both this semester and next semester. We're ultimately going to learn about how all of these functional groups behave and what you can do with them and how you can use them to make useful molecules. But all of these functional groups are used constantly in pharmaceutical industries and materials industries in order to convert them into whatever kind of molecules that they may need. So first of all, in terms of the carbonyl-containing functional groups, I think it makes sense to start with the aldehyde. It's a funny word, A-L-D-E-H-Y-D-E, aldehyde. And I would say that aldehydes can be defined as R, then a carbonyl group, then a hydrogen. So that's your basic definition of an aldehyde. And for an aldehyde, it is okay if R is hydrogen. So the simplest aldehyde is CH2O. And I think you know that guy, that's called formaldehyde. If you then changed one of those hydrogens to anything else, I'm running out of room, so I'll write it like that. But you see what I mean? You may well come across a question where it's pointing in a different direction, or maybe for whatever reason they feel like writing it on the other side. Put a benzene ring on. I would expect you still to recognize that as an aldehyde. So you don't want to be memorizing them as being in any particular locations. You see what I mean, how all of those are aldehydes? So aldehydes are a very commonly used synthetic starting material. You know how formaldehyde smells. And most aldehydes smell kind of like that. They're mostly really unpleasant. With one interesting exception, this guy. If the R group is a benzene ring, we call that molecule benzaldehyde. You'll learn that eventually. I don't care if you know it right now. But for some reason, benzaldehyde smells quite lovely. People do disagree as to what they smell when they smell benzaldehyde. Some people say maraschino cherries. Some people say almonds. But pretty much everyone agrees it smells wonderful. Who knows why? Just how those smell receptors work and how things fit into those receptors. Who knows? Very strange. Nuclear smell. Well, that would, that is also nice, but that is not benzaldehyde. I guess it would be weird if your car smelled of benzaldehyde. Good, so much for aldehydes. Let's now take care of ketones. It's good to do those almost in the same breath. Spelling, functional group spelling, pet peeve number 2. There is no Y in ketone. Please and thank you. Ketone. But I do get that all the time. It sounds like a 50s band. Ladies and gentlemen, the ketones. No, there's no Y in ketone. And ketones are similar to aldehydes in many ways, except we're going to have 2 R groups. And here, of course, neither R1 nor R2 is hydrogen, can be hydrogen. And I would think that's a separate thing that you need to memorize. I think if you look at that, you know, imagine replacing either of those R groups with a hydrogen. You want to have a ketone, you'll have an aldehyde. See what I mean? So I don't think you need to memorize that extra. So both R1 and R2 have to be alkyl groups, but they can be any alkyl group. They can be the same or different. The simplest possible ketone would be acetone. And those of you who are taking lab, at least in person, will use acetone quite a bit. It's a very commonly used solvent. We use it to wash glassware. It's pretty benign. I wouldn't go drinking it. I wouldn't go taking a bath in it for sure, but it's pretty benign. It's fine to use to wash glassware. But again, the alkyl groups in question can be anything. That would certainly also be a ketone. So can you all see the C double bond O over here? The ketones can be cyclic. That's certainly allowed. That guy happens to be called cyclohexanone, cyclohexane-one. And we'll learn that eventually later. I'm only mentioning this for now just so that you know these things do have names. But anything like that would qualify as a ketone. Make sense? Questions? Let's see. We need to do carboxylic acids, amides, and esters, and then I think we will be done with functional. I mean, there are other functional groups that are in the table. I don't think we'll have time to go over every single one of them. I would say you need to know all the ones in the table, and by the way, there are dozens and dozens and dozens of other functional groups that are not mentioned in the table. And we will eventually meet one or two others. But I think the ones I'm going over here in class are going to be the ones we'll see most often, but you certainly are responsible for all of the ones in the table. And you can learn them in the same way. So, carboxylic acid. Carboxylic acid is a very important functional group. And actually, I think the other day we were talking about acetic acid. So that's certainly a carboxylic acid. We could define carboxylic acids as R C double bond O OH. So it's a carbonyl with an R group on one side and OH on the other. Now, carboxylic acids are not alcohols. When we defined alcohols, we said that the carbon directly attached to the OH oxygen had to be a hydrocarbon type carbon. This is not a hydrocarbon type carbon. So that's why there's no contradiction. So I mean, sure, they both have an OH group. There are some similarities between alcohols and carboxylic acids, sure. But they also have significant differences. One of which, as you probably will have already guessed, is carboxylic acids are a good deal more acidic than alcohols. But carboxylic acids and alcohols are different critters. So it is allowed for R to be a hydrogen in this case. That compound happens to be called formic acid. You find that in like bee and ant venom and things like that. So it's very, very irritating. Certainly acetic acid is probably the most well-known carboxylic acid. You find acetic acid also in vinegar. Vinegar is pretty much any kind of vinegar you can pull off the shelf. It's probably 4 to 5% acetic acid. Again, you can attach any kind of functional group or any kind of other carbon group you like. Let's go crazy and put a benzene ring. Oh, and let's just put a methyl group on the other side just because we can. That would certainly also be a carboxylic acid. Oh, also, just so you're aware, the group itself, the C double bond OH, that can be abbreviated as either COOH or CO2H. You will see those as well. And I don't care if you use those abbreviations. I just want you to be aware of what they mean when you see them. I'm kind of a CO2H guy. I tend to write it like that. If I'm talking about something where all of the bonds and electrons and exactly where they are is not really important. And I just want to express that we've got a carboxylic acid. So it depends what you want to say. Good, and I think that's about it for carboxylic acids. Let's then do esters. Third and final pet peeve, there is no H in this ester. This is not the biblical ester, E-S-T-E-R. And they're kind of like carboxylic acids. They really are kind of a condensation product of what you would get if you stuck together a carboxylic acid and an alcohol and you removed a molecule of water. Next term, we'll learn how to do that. But an ester is defined as a carbonyl with an R group on one side and OR on the other. And the two groups can be the same or different. This group R1 here can be either H or alkyl. Both are fine. R2, I think you'll see instinctively, must be alkyl, cannot be H. Because if it were H, you wouldn't have an ester, you'd have carboxylic acid. So it's not something you have to memorize separately. It just kind of makes sense. So the simplest esters would be your formate esters if R1 is hydrogen and R2 is, say, methyl or ethyl. Probably the most famous ester, the one that's used the most in consumer products, is the ethyl ester of acetic acid, which we call ethyl acetate. You find that thing in like paint thinners. I think nail polish remover has some ethyl acetate in it. I can't say I've ever used nail polish remover, but I'm told that it has ethyl acetate in it. But again, these things can be arbitrarily large, and the two groups on either side can be the same or different. Both are allowed. And then, last but not least, the amide functional group. And amides are amides are kind of like esters. I would say amides are to amines as esters are to alcohols. And I really do think the best way to define an amide is like this. I'll do it kind of the way I did with amines. So you've got a carbonyl group with an R group on one side and a nitrogen on the other. These other two bonds to nitrogen can be to either hydrogens or alkyl groups, doesn't matter. They can be anything, either hydrogen or any alkyl group, any hydrocarbon group. But you do have to have this one carbonyl group in order for it to be an amide. And so I suppose the simplest amide would be just all hydrogens. Yep, that's a thing. Call that form amide, or don't. I really don't care if you know these. We'll learn how to name amides much later. But again, the R group and the other groups attached to nitrogen can be whatever you like. You could have a benzene ring here, let's just say. And then maybe ethyl groups attached here, just because. And again, those two groups attached to nitrogen can be the same or different, doesn't matter. I would expect you to recognize it if it were pointing the other way. Right? Don't get married to everything always facing in a particular direction. I mention that because it's something I've noticed over the years that it's a trap that students can fall into. Please don't fall into that trap. So I would expect you to be able to recognize that as an amide as well, and also an aromatic compound, by the way. So it's both. And like I said, there are other functional groups that are in the table. Take a look at them. I think you can learn them in pretty much the same manner. These that we've gone over here are overwhelmingly the most common ones that we'll be dealing with. Let me just also tell you what's coming up in the next few sections. We've already talked about isomers a little bit, I think, and constitutional isomers. So I think we're all right with that. Alkyl groups are something we're going to use when we start naming alkanes next time. Methyl, ethyl, you've heard me use these names. I really do think the only alkyl groups you run into are going to be up to 4 carbons. So you've got methyl, you've got ethyl. There's 2 types of propyl groups. There's normal propyl and isopropyl, because there's actually isomers there. And then there's about 4 types of butyl groups, the most common of which are normal butyl and terbutyl. We actually had a terbutyl group earlier, tertiary butyl. So, but I would leave you to learn those on your own. I think they're in the textbook. And I mean, I wish I had time to go over everything in class. I just have to sort of focus my time on those things that in my experience need the most explanation. Another thing to take a look at that's also in section 3, and I'm sure I'll be touching on all of these as we go, but this whole method of categorizing carbons as primary, secondary, tertiary, and quaternary. And I gave examples in the class notes, and I defined all those things also in the class notes. So I wish I had time to go over examples of all these things, but I'm already out of time. So that, though, I think puts us in a good place to be ready to name alkanes when we come back on Monday. I'll just point out that in the class notes for section 4 of this chapter, I've listed out one way of going about naming alkanes. It is not the only right way, but it's a step-by-step method that you can use. Certainly feel free to adapt that to whatever works well for you. So hopefully everyone's registered your attendance. I'll leave that up for a few more seconds just in case. But other than that, have a great weekend, get some rest. We'll see you Monday.